So what is cross validation? I explained you, once you train a model, you apply the model on the unseen data, which is nothing but in our case, it is a test data set. That's what we are saying, right? So and then we apply the model on the unseen data, and then we see how well my model predicted on the test data set. So using the score, we found, so both the training and test data score was more or less same. Hence, and also the score was slightly on the higher side, 0.90 or something like that. It is somewhat closer to 1, and we concluded that model was good. Okay. Let's say I have a situation. Okay, I have a situation. Let's say I have a train and test set. Train and test set. Okay, so we apply two different models, to these sets. Okay, I'm applying two different models. Like I said, model 1 and model 2. Model 1 has only two independent variables, and model 2 has, let's go by the same example. Okay, 4 independent variables. Or let's say, I'm going to say model 2 has 2 independent variables. I have 4 independent variables here. When I used one train and test set, for this, my model A performs well. Like you said, right, Gilbert, you asked, can I change the test size instead of default 75-25%, right? Can I change it to 60-40 or 70-30? Yeah, you are using different training and test set, but your model 1 performs well on that training set, but the model 2 was not performing well on that data set. Okay, see, the model A performs, model 1 performs better than model 2. But in reality, model B is superior than model A. Because we are, this model performs well on this given train and test data set, but this model 2 is not working well on this given train test data set. Or let us put it this way, let's you are giving me the training test data set. Let's Palani has given me the Palani. I'm going to ask you a question. Okay, Palani is going to give me the train and test data set. See, the data set was given to Palani by his customer. He splitted this into two different set, train and test set. Train is usually more, right? So let's say 70-30%. 70% of data randomly is sampled from this data set. That is my training set. Remaining 30% data is test set. My model 1 performs well on this training and test set. That means the score for train and test set for model 1 is more or less overlapping, is good. But model 2, when I do this, it is the accuracy is not good. Okay. Now what happened? And now let's say Mala, she gives me another train and test set. It is slightly different from this one, but with this, my model 1 is performing very well. Sorry, model 2 is performing well. Model 1 is not doing good job. There is some kind of we reach some kind of we are not able to reach any conclusion in this case. With this train and test set, my model 2 is performing well. With this train and test set, my model 1 is performing well. We are caught in between, right? So now the situation is there any way I can use the every data as a training data set, every data as a training set, and every data as a test set with the given data set? Okay, so that is where we have something called k-fold cross validation. So what we are doing is, in the k, you can specify the value whatever you wanted. For example, 5-fold cross validation you can do, 10-fold, and 20-fold cross validation also you can do. So usually in general, 10-fold cross validation we use it. For example's purpose, we take 5-fold cross validation. Let us assume that in your data set you have 2,500 records are there. We are splitting into we are creating 5 folds. Okay, and each fold we equally divide this data into 100. Which you have 100, 100, 100, 100, 100. So 500 into 5, 2,500. Right? You split the training data. So I'm talking about the training data. The training data, you have 2,100 records. We are splitting the training data into 5 equal parts because it's a 5-fold cross validation, 5 equal parts. So what we are doing is 5 equal parts, how much? 2,500 divided by 5, how much? 500, right? So each fold you will have 500 records. And also in each fold, you split the 500 into 5 equal parts. So 100, 100, 100, 100, 100. So split the training data set into k equal parts. In this case, 5 equal parts. So 1, 2, 3, 4, 5, 5 equal parts. This is my training data set. Okay, we splitted this training data set into 5 equal parts, and then we are going to fit the model on k minus 1 parts. In each fold, what we are doing is k minus 1. The total training set is k. Let's here 5, right? 5 groups of data is there, minus 1. I'm going to exclude this one. Excluding this one, the rest of the mark considers a training set. Look here, this diagram shows very clearly. 400 records, I will consider as a training set. Remaining 100 record, I consider test set. See, this one is applicable in case the data set given to you is less volume of records, right? The training data set itself, you have less number of records. In that kind of situation, you can go for k-fold cross validation. What we are doing is we are splitting the entire data into 5 equal parts. And then here, first 5 records, the 5 set of records, you consider training, remaining test set. And if you come back to the second fold, I call this as each thing as a fold 1, fold 2, 5 folds we created. Fold 3, listen very carefully, very simple and interesting one. And fold 5. All right. So 5 folds we created. And here the second fold, what we are doing is, so here also we have 100, 100, 100, 100, 100, 100. This time what, this algorithm does is, it excludes the second last group, okay? And then remaining 4 groups is considered training data set. This one is a test data set. Similarly, when it comes to fold 3, it takes these values as a training data set. This is a test data set. Okay. And similarly, this one considered test, and this one is again rest of them are training data set. So in that case, we make sure that every data we consider as a training data and test data set, right? So when it comes to this fold, so in this fold, whatever we consider training data, it became a test data set. In this case, whatever we consider in the previous folds as a training data set, we are considering as a test data set, right? So what we are doing, we are taking the same model, and then we are running that model against this training and test set, 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 against this training and test set. So 5 folds, you have 5 different training and test set. When you run your model on these 5 different training and test set, each time when you run your model, you'll get error, right? Root mean square error. Let's say your root mean square is something like this. Let's say your root mean square is 1.2. And in this, for here, the training and test set is different. Here is 1.8. In fold 3, you are getting 1. And here you are getting 2.8. And here you are getting 1.6. If you look at all these values, if you take the average, right? So if you take the average, so what you will get, that is what your mean squared error. Or if you take the average of the error, mean error, right? So 1.2, 1.8, 1, 1.6. If you look at this, right, these are more or less somewhat close by, whereas 2 point is a little bit different. You need to take the mean on these 5 folds error, and then you take the standard deviation. How many of you remember standard deviation? Higher the standard deviation refers what? What is higher standard deviation? If the value of higher, let's say you are computing the standard deviation, if the standard deviation shows higher value or lesser value, what does it tells us? How many of you remember? Personal, okay. Higher the standard deviation tells us higher the variability, higher inconsistency. Yeah, that is what I've been talking, right? I've been asking, right? Higher standard deviation tells us higher the variation. Lesser the standard deviation value tells us low variation. Right? Lesser standard deviation value tells us it's a low variation. Okay, the variation is less. So now you tell me approximately, just by eyeballing this, can you tell me what will be the variation? The variation will be low, right? Because more or less all the values are somewhat close except this one, right? Except this one. So if I execute the same model with the same independent and dependent variable across different training and test set, still my model, the error is variation is less. Okay, and if the standard deviation variation is very high, so that means my model is not generalizing well. If you give different training and test set, my model accuracy should be consistent. The same example here in the college, even if you give the different question and answer, tricky question, still I should be able to answer it. The model should generalize well, right? So this is called something like, there is a bias variance trade-off. What is bias? Bias is, you just think bias is something like, error. Variance is something like, the how, with the different training and test set, how well your, error is varying. If the error is not much varying, that means your model is good. So you have, low variance. See, in the ideal world, low variance, low bias is expected. Low bias, low bias, low variance. But this is not practically possible. We are not living in the ideal world. Okay. So low variance. That means even if you execute my model in any training and test set, the error variation is not much. Everything 1.2, 1.1, 1.2, 1.3. If all of them are somewhat similar, that means the variance is less. That is what your standard deviation. And if you take the mean, obviously, right, so it comes out, maybe your error is more, right? Or error is moderate, right? So you have moderate bias. And importantly, the variance should be less. Okay. So the variance at least should be medium. Okay. Too much of variance is there. For example, if I run my training and test set here, I'm getting 8, error is 8. Here I'm getting 12. Here I'm getting 2, 1. Just because my model is performing well on this training test set, with this in training and test set, the error is too high, too much of variance. That means my model is not generalizing well. It is memorizing it. With the help of cross validation also, we can check, because we are running our same model against different train and test set. Okay, with the different training and test set, can we see any difference, too much of difference? No, we don't see too much of difference. That means you are safe, right? You can deploy the model in production. You can deploy the model in production because you don't see any, but still we compare with different algorithms, neural network, and then gradient boosted regression, right? All these things, random forest, we test the same thing with different algorithms. Of those algorithms, which one has low variance, low bias, right? Then it is good to go ahead and deploy it in the production. Because in the production, we don't know what data are coming every month, right? New data will be coming in. Once you deploy your model, that model will get applied on the new data. Okay, and your model should predict well on the new data also. If the model is not able to predicting well on the new data, what will happen? Whatever effort you put it in terms of developing the model, deploying is completely waste. So make sure that how well your model is generating well. This is called your cross validation. So what I do is, in the interest of time, I directly jump into my, what is the time now? It is 7:57. I directly jump into my other thing, which I already developed it, put it here. See, we cannot say, Gilbert had a question, how much time it will take to develop model. It depends on the volume, depends on so many factors, number of features, all the things, okay? And look here, this is the k-fold cross validation. So like I explained it here, right? So how many folds you can create it, you can specify it here. We have something called CV, cross validation equal to 10. In this case, it will split the data into 10 different folds. Here, fold 1, fold 2, fold 5, and 10 folds. This is the standard that we use, CV equal to 10. And then we have a function called cross val score that is available as part of your SQL and model selection. Then you need to specify your model name and the training and test data set, dependent and independent variables, and which scoring method. So here R squared, you use it. And for each fold, it gives me different R squared value. Look here, this R squared and this R squared, more or less good, but this is very less. Is going down, right? So, but the rest of them are fine, but still there are some variation here. You need to find out the standard deviation, everything, okay? CV10 is nothing but the cross, how many number of folds that you need to do. 10-fold cross. This is 5-fold cross validation. Likewise, 5 more folds will get created. The same model will get executed, run against each and every fold, 10 folds. And each fold, what is the R squared value? You can also use RMSE. The scoring different methods are available. Here I used R squared, and you see it. And end of the day, variance. If the variance is less, and if you are reasonably less, okay, we cannot say less, reasonably less, and if the bias is also reasonably less, even if the error is a little bit more, and the variation should not be there. If the variation is there, then you are gone, right? So that is the thing that you need to understand as part of cross validation. So there is a trade-off between bias and variance. That is why I called you. They call it as a bias variance trade-off. Bias variance. Even if there is a error, little bit error, right, and the variance should be less. So there is a trade-off here. Okay. So there is a trade-off here. So trade-off in the sense, the error is slightly more, but the variance is good, but the error is slightly more. With the slightly more error, almost all the folds, it's all matching. Somewhat it is close by. Variance is okay, but bias is more. Let it be there. By end of the day, variance matters, right? But again, bias should not also be very high. Okay, if the bias is slightly high, but there are no variants, then you are safe. Okay, that means the model is generalized well. Okay, so fine. But again, you try with different algorithms. Okay, each algorithm right uses so each type of algorithm, each algorithm uses different techniques, right? So in that formulas, so in that case, what will happen is there are some algorithms it can boost your the performance, okay, and in terms of reduce maybe less, it reduce your bias and variance also little. Let's say if it is consistent, the error is consistent across all things, then you are safe. So now you understood, so this is the situation. I started with this situation, right? Model 1 performs well with the this training and test set, but model 2 is performing well with this training set, whereas the model 2 is not perform well on this test set. You are in some kind of dilemma. So in that kind of situation, if you create 5-fold or 10-fold cross validation, if you run your model, so let's say I'm using 10 different training and test set to run model 1 and 10 different train set I used to run my model 2. With all these things, which one is as a less bias and less variance, or slightly even if the bias is slightly high, the variance is not much, then that one is the best model. So in this case, you cannot go by this. So you will be worried, right? So model 1 is performing well on this training set, whereas model 2 is performing well on this training set. So if I apply the model 1, it is not doing good job. So now you caught in between so something, right? So you are in dilemma. So can I use some other train and test set and test these two models? So how many train and test set can I use it? You can use 5-fold or 10-fold cross validation. If you use more train and test set, you are pretty confident, right? It's something like when you take up more quizzes in the exam. Before exam, if you take more quizzes, if you practice well with more problems, so you will develop more confidence, right? The same thing is applicable here. Okay, so iterations here, say 10 iterations for model 1 because you're using 10 folds. So in this case, 5 folds and 5 iteration for the same model. And the model B, you are running it for 5 different iterations. Now you understood what is iteration here, right? Yeah, the same model you are running it 5 iterations because we have 5 folds, and each iteration, what is the error? Take the average and take the standard deviation for model 1, model 2, and whichever model has lesser value, that is the best one. You can do it that way. But there are cases, even after using 5-fold cross validation, even after doing the feature selection, everything, my model performance is not good. Try with different models. Some cases, what will happen is your data set will not have pattern at all. If you have very less number of data, it will not have pattern in it. That is a different thing. But now you understood what is cross validation, k-fold cross validation. If the